Okay, that's yours, correct?
Thank you.
Okay, so
Yeah.
we're gonna finish talk about the reaction of amino acids. Then we're gonna go over the exam paper a little bit. So let's talk about some topics today. We want to talk about the chemical reaction of amino acids. Some of that, okay, not everything, some of them in the textbook we want to mention. So first thing, how are we going to measure free amino acids? And there is a way to do. I believe in the chemistry class you guys learned. So we can do is a color spectrometer at 570. For most of the alpha amino acids, it will show a purple color. And this purple color, we also call it Lohmann's purple. Now for the beta amino acids, that could be showing you a pink color or orange, pink to orange. Okay, we just say sometimes pink, a little bit orange. We just say orange, orange color. Now there's a little bit difference is if we are talking about a proline or a hydroxy proline, then the wavelength should be 440 nanometer, and it will showing you a yellow color. So that's a little bit different. This is going to be yellow color. So why? Because if we know the structure of proline and hydroxyproline, there's some difference. So let's talk about the proline. If we review, this is amino group H, carbo C, and carboxy COH. Then for the proline is CH2, CH2, go here, CH2, CH2. So it's a circle. So that is, we call this a proline. Because lots of the other amino acids are not. And then we talk about the hydroxyproline is here, you add OH. So that's why it's a little bit different. Now the question, since we are for chemistry class, why we can do that? Because there are some of the chemicals we can use it. Now obviously, before we do, using the color spectrometer, we have to do some of the reaction. So what's the reaction we have to do? There is a very important chemical, which looks like this. That's a carbon. You have a double carboxy, and then you have hydroxy bonds. Hydroxy there. This is called 19-hydrine. The 19-hydrine will work with, reacted with amino acids. That's NH2, C, O, H, and COOH. So what's the reaction will be? I want to save some place, so I'll just do that like this. Now obviously you will see there is a aldehyde that comes out. There is a carbon dioxide that comes out, and there is ammonia comes out. These are pretty obvious, but what will cause the color change is this big one right here is, we have to draw like this, okay? Go here, in. That's, and you have this guy, the nitrogen comes. Here, it's very interesting. You can draw like this. You go here, go here, here. So just simple to do like that. This goes here. This chemical will show you the purple color, the Lehman's purple. This is called hydrogen dentin. So that's what's the story behind it. If we dig a little bit more, talk about the chemistry. Okay, so that's the first thing first we want to talk about, measuring amino acids, which means an amino acids, you're working with a reagent called 1900, and then will reacted, generate a very important chemical called hydrodentin. And this hydrodentin, the products you measured at wavelengths 570 nanometer, we can see if it's purple color, then it's amino acids. It's alpha amino acids, which means the product has 3 amino acids. And specifically, if it's proline and hydroxyproline, we change the wavelengths to 440, then you show the yellow color, which means the product has proline or hydroxyproline. So these are the very basic measurements of for the free amino acids. Okay, the second reaction we want to talk about is, we call it racemization. Racemization is very common during the food processing. So we mentioned about the amino acids. Majority of these are L amino acids. If during the food processing, what happened is there is an alkaline agent present, and also with extended very high temperature. Let's say sometimes more than 200 degrees Celsius. Then the L amino acids will become D amino acids. And also sometimes they will generate a carbonium, which is a byproduct, and also could generate a dihydroalanine. We call it DHA, but it's not the DHA where we're going to talk. Go to the lipid section. So that's what happened. Now, once this happens, what's the results will become? First of all, we talk about the most important amino acids in our body is those essential amino acids. They are L configuration. If during the food processing you working with a very reactive hydroxy agent or extended heating temperature, they will lose, become D amino acid. So the first thing they will lose, essential amino acids. That's the first bad thing will happen. The second thing what will happen is, the D amino acids, it is less digestible. So in other words, they are not very efficient to be digested by gastric protease, which is an enzyme in the intestinal or stomach area. Number 3, they could potentially have a toxication will generate. So the research has been showing if you're feeding somehow 50 to 100 parts per million D-proline, you may well get neurotoxicity logical toxin in chicken. So I don't know how they do it, but they didn't describe the very detail, but maybe they do the feeding, and after do the feeding, they do the kind of like a CT scan or something. We'll see the structure of the neural system, the brain system to see that. So that's something really bad happens for the racemization if it's happened. Something else we want to talk. We talk about this as a chemical reaction for amino acids, but it's very interesting to see is that the racemization is very easy to happen as amino acids in peptides as part of protein. So the chance for free amino acids in a peptides as part of the protein is much higher than a simple free amino acids. So it's very interesting. If this amino acids is in the protein, it's easier to have racemization compared to you just have a free amino acids from somewhere. And the reason is, we talk about the reaction energy. If amino acids in the peptides and also as part of the protein, they have somehow have an intramolecular, we call it bond connection power, we just say that. And this power will low down the energy required for the reaction. But as a simple free amino acids, they do not have that advantages. So amino acids as part of the protein is much easier to happen racemization compared to a free amino acids. Okay, so we talk about all these other conclusions. We just want to mention something, the structure, how it's explained. So the structure will be, I have amino acids like this, okay? This is H, this is COOH. We're going to draw CH2, this is X, so just like that. And one day during the processing, we got an alkaline reagent, okay, alkaline agent. And the temperature is more than 200 degrees Celsius. Now, by the way, when this reaction happens, the concentration of the alkaline agent obviously is important. So we can add one here is concentration of this alkaline obviously is higher, the more easier to have the reaction. So what happened is, what they do? They are attacking right here, ZH. Okay, when they happen attacking here, they're going to be reacted. So once they reacted, they create these products, CH2, X, COOH, and 2 dots. Because the H is gone. This is called carbanion. Now, once this carbanion generates, they go 2 different directions. They could go this way. With the assumption, during the food processing environments, you have acid. It happens very often. All the food products, you have chocolates, fatty acids, egg mayonnaise, all these things, milk, they have more or less have some acids. So this is going to happen. Okay, once this happens, what they do? They put them back. So this H is back. But what's the difference? This CH2X, the units is turned around, so the configuration is changed. So this goes up, become CH2X. What's the difference between this guy and that guy? This is L amino acids, and in here, this becomes the D amino acids. So that's what happened. You have racemization happens at the same time in the environment. You may have acid. This process we will mention again. It's very similar to the fatty acids happened hydrogenation, which means you have double bonds in the fatty acids. Then you add the same thing is H, which is a proton. When you add a proton, you try to make the unsaturated fatty acid saturation. However, the configuration will change. The idea is the chemical always want to make at a lower energy status. Because they change the configuration, they can keep the lower energy. And they will let the reaction happens more efficiently, require lower energy to do. That's why they change the configuration. So from the L to the D amino acids. Now we have this carbonyl. They could also go this another direction. Another direction we can go right here. So what happened? NH2, C, COOH, there's no difference. However, this becomes a double bond. What's the name of that? Dihydroalanine. That's DHA. I will write quotation mark DHA. Then what else? Obviously, this X is released. So this guy comes out. Now, once this guy comes out, in the food system, they will react it with lots of these residual amino acids will create cross-linking. This cross-linking system also not very good sometimes. So we're going to mention the second topic is cross-linking. Okay, so the third topic will be amino acids cross-linking. Now, by the way, there's one thing we haven't forgot to mention. We have 20 L amino acids. Racemization could happen for all of them. But basically, asparagine, glutamine, serine, cysteine, 5 or 6 of them are more easily to happen compared to the others. Here is the same thing. Once this DHA created, the cross-linking system will be created during the food processing. It's also a couple of the amino acids are much easier to happen compared to some others. There are 2 amino acids is well recognized, will happen during the food processing is, the first one is cysteine. So we want to talk about this guy. Okay, cysteine, what happened? We need to know the structure. So cysteine, you see the S there, which means they have sulfur group. So I want to make sure it's correct. Okay, now we have this DHA there. Here you have a double bond CH2 and COOH. So this is DHA. What will happen? That's very interesting is this guy here, will attacking the sulfide. Then the sulfide will go ahead to attacking the CH2, which is a methyl group, and further they were attacking the chiral C. they will be attacking with each other continuously and will form the cross-link. So what's a cross-link will be looks like? We have to put it upside down. So CH, COOH, you have CH2, you have S right here. So you have S right here, this goes here, is CH2, equals C, NH2, equals COOH. There is a typical name for that called lasso anion. That's a minor product. We don't care that too much. What we really care is another disulfur amino acids. So cysteine is a sulfur amino acids because it's a sulfur bond. We have another one, which is two cysteines they combine together. So we're gonna draw here, okay, yes. NH2, CH, COOH, CH2, you have S, you have S, you go here, CH2, C, NH2, COOH, you have H. This chemical is two amino acids of cysteine, they combine together. If you can see, very simple. Looks like this, and these connect together. What do they call? Cysteine. Okay, once the cysteine happen, in the alkaline environments, at more than 200 degrees Celsius, they will be directly, more efficient, directly become a DHA. Now what happened? There is amino acids widely existing in dairy products or even in the milk is lysine. So what's the lysine looks like? So lysine looks like, I'm gonna draw right here. NH2, CH. It's a very long CH2. CH2, CH2, maybe like 4, CH2, then NH plus. So that's lysine. Lysine, you see this is a very long CH2 chain. It should be 4, let me see, so yes, 4. And the NH3 is at the top. This is we call epsilon amino acids. And they provide a lysyl residue. Okay, once this happens, lysyl residue, they could be reacted. If these two reacted, what will generate? It's not very difficult. They will generate NH2, CH, COOH, CH2, CH2, very long, CH2, and because here you have NH, CH2, you go here, C, NH2, COOH. There is a special name for this guy. There is a very typical name for this guy. This is CH. Lysyl alanine. I want to make sure lysino alanine. LAL. So people doesn't recognize it. Lysyl alanine is a major cross-linking system in the food products during the food processing. Once this LAL happens, some trouble will give. Number one, very similar. Less digestible. So what happened is LAL may be absorptive, but hard to digest, and eventually become urea. Exudative, we can say. So when you take off the urea sample, you're taking LAL out. The second one, people did it on the rats. So in the rats, what they do, they are feeding 100 parts per million LAL. And what they find, last time they find, you may have like a neurological toxin in the chicken when you have a deproline for the racemization. This time the cross-linking happens. If you are feeding the mice, the rats, 100 parts per million LAL, you may have kidney disease. And we call it nephrotoxic. And it has not been do some research on the human being, but it's already been found about that. Less digestibility, yes, that's what we mentioned. Now, why I want to say this is important, because lots of people did the research. This happens all the time. Lysine is a very important essential amino acids. They try to see the LAL content in various food products. And what they find is very interesting. So the first one, let's say we have a potato chips, corn chips. So we have corn chips. The amount is high, 390 microliter per liter. That's ppm, parts per million. And they also find that in a predator, that is more than 500. At tortilla, they find 200. Tortilla, around 200. Taco Bell, around 107. So that's widely existing. Looks like when you eat these fast food, you absorb lots of the LAL, and they go out of your body, become a urine sample. Now, there's one thing people find more interesting is if a milk, you're using high temperature, short time treatment, that could be somehow about 300 to 1,000 ppm of the LAL. And they also find if it's skim milk treated with heat, or we say evaporated, that could be more than 500. But there is one we don't have it, is milk powder. Milk powder is basically close to zero. So what this tells us, this partially explains, we don't recommend you the milk to heat it or to boil it. So we talk about the raw milk we shouldn't drink, because raw milk has lots of the microorganisms there, especially like microbacteria. Microbacteria phenol, which is could cause a bone, the debone, or the hunchback, which means they're not going to absorb the casein very well, calcium very well. So lots of people think about we're going to kill the bacteria, so the milk powder or the raw milk, we go ahead to using a high temperature to heat it, using microwave. Now you may not reach 200 degrees Celsius, but you boil it, reach to 94, 100 degrees Celsius, so more or less what happened. Because the casing is a major component in the milk. So you're going to lose the casing. And at the same time, you have created lots of the LA air. And you look at here, they potentially maybe have a kidney disease. And it's not really sure, because there's a dosage, but it's at least it's less digestible. So looks like if the milk you boiled for a long time, maybe you think it's a safety issue. You solve the problem, but it's less digestible, and finally it's becoming urine sample comes out. It doesn't help at all. So that's something interesting to know. And also these fast food, you can see these are lots of the LAL components. And we also mentioned Maillard reaction. And these color change could be related to the Maillard reaction, could generate acrylamide. That's another issue for that. So here you can see it's very interesting. There are lots of the side chemicals, not good chemicals generated in those fast foods. Now during the food processing, because the lysine will react with this DHA, so you could sometimes add ammonia. You could also add somehow like sulfide chemicals to compete it with epsilon amino acids from the lysine. Then instead of lysine reacted with DHA, these chemicals reacted with the DHA partially can prevent the LAL generate. But that's somehow needs to be validated during the processing, because all these things may affect the quality of those foods. Okay, so that's something we mentioned in the textbook. I just want to say. Another thing I want to mention that textbook mentioned an experiment using bovine plasma albumin. They said the bovine plasma albumin heating at 115 degrees Celsius for 27 hours. I think it is 2.7. I don't think it's 27. That will makes the whole swimming pool evaporated if you do like that. I think the experiment will be doing like 2 or 3 hours. That's a very high temperature. So what they find is that this product has higher amount of lysine. That's not a problem. We already mentioned. So you have this guy right here. You have this CH2. I'll just write 4. NH3 plus. They also find they could have asparagine or glutamine. So asparagine and glutamine are very similar. There is only one difference: is the methyl group is CH2 is one, another one is 2. So they write CH2 like N, and this goes O, this goes NH2. So if N equals 1 is asparagine, is N equals 2 is glutamine. This could react it. First of all, the amino base is gone, so generally the ammonia, that's not a problem. The other thing will generate a very, very long chemical. That doesn't have a specific name there, and we could draw for you, which is NH2, CH, COOH, CH2 4. Then you go here, will react with NH. Okay, then you will react with an NH, then you have a CH, so you have a C, NH2, H, and COOH comes out. This experiment tells you these lysine, if they are present in the texture plant protein, if you heat it for extended time, the lysine could be gone, and the asparagine glutamine could be gone, and then become a huge cross-link. Because right now, the plant protein research has been done a lot. They are thinking about this will be a good replacement of the meat in the near future. So lots of the research has been done that, but you have to be careful. Extended heating at high temperature, the cross-linking could happen. Then you lose basically the essential amino acids. Okay, so this is some of the examples. Just want to show that to you. Next topic we want to talk about is oxidation. So oxidation of amino acids. We know there is a lot of the oxidation reagent. During the food processing, we cannot avoid it. For example, chlorine, hypochlorous gases. But more often, what we have is hydrogen peroxide. Since we are talking about here, we can talk about something we did in the lab, hydrogen peroxide. Another thing what we're using often is peri-oxy-acetic acids. So what's a peri-oxy-acetic acid looks like? That is a reaction between acetic acids with hydrogen peroxide. So what's that? This is acetic acids, and that is hydrogen peroxide. If we go there, we will generate a very huge, a high oxidizing agent. They say like here, this O is the key, then COOH. This guy here is the key. That's peri-oxy-acetic acids. Now, if we have a compound, this is 23.5%, this is 5%, you combine this, this is we call candidate 5.0. That's what we did in the lab for the antimicrobials. Because we have we have oxidizing effects for the bacteria. But these chemicals, during the food processing, they were added or they will be existing. Or sometimes, even there is an internal oxidizing agent will generate. So basically the oxidizing of amino acids, you cannot avoid it. So that's why we give you some of the examples. Now, very often they will happen is happen at several chemicals, which is methionine, they could happen. Methionine, they could happen. Cysteine could happen, and tyrosine could happen. If cysteine will happen, then cysteine obviously will happen. So we just give you several examples to see what are they. We have a methionine. So we need to know the structure of methionine first. Methionine, NH2CH, COOH. So we have a CH2, CH2, S, CH3. That's methionine. Methionine, you see the sulfur there? So, what means? That means there is different scenario could happen. So I'm not going to draw the whole thing, okay? What's the scenario will happen? It could happen, you only add one oxygen there. This with reaction, 0.1 mole hydrogen peroxide. You gotta get an O there, which is oxidized one time. So that could be become this guy. This is called methionine sulfur oxide. Then it's easy. The second scenario, you could add another O there, which means you further reacted with 0.1 mole hydrogen peroxide. Then another O could be there. So it becomes OSO. This is what we call methionine sulfur foam. Then further reacted. If you have more and more hydrogen peroxide there, what will happen? This whole thing will go down. This here will be changed. Instead of you have that, you replace with a hydroxy bonds. So this will be changed, looks like O, S, O, and on the top become this. This is cystatic acids. So that means I'm methionine, which is amino acids, essential amino acids. At the end of the day, you have cystatic acids, which is completely gone during the huge amount of the oxidizing amino acids. That means the packaging is important for some of the products because that's completely gone. Why? These two basically is unreversible, and this is, we say, hardly digestible, or we say biologically unavailable. So it's like a waste. Okay, so that's for MBT. Then let's talk about the cysteine, what will happen. So we have a cysteine. We already drawn a couple times. We have H2, CH, COOH, CH2, SH. Now this time, the attacking point is here. So still three different scenarios. I help so you to remember, we have an agency called OIE, Regulation Veterinary Science. If you switch it, become EIO, then you can be remembered. If the top SH becomes, the first scenario, this becomes SOH. This is called cysteine sulfur phenic acid. Then, if the SOH becomes SO2H, this is called cysteine sulfur phenic acids. If the last one would happen, it becomes O3. I don't think there's an H there. Let me double check it. Okay, there's H there. Then become cysteine terms of formic acids. And you can see the only difference is this is E, this is I, and this is O. Okay, so it depends how many oxygen base they added. Cysteine, this one happens. There's a little bit difference. This reaction here is at 0.1 mole hydrogen peroxide. This will happen is in a very acid environment. This is more than 1 mole. Will happen. Having the appropriate amount of the acid is also important because acid will be drawing the oxidation amino acids. This is lots of the time people will add because you can lower down the pH. We want to lower down the pH to, sometimes we want to control the moisture, so we sometimes lower down the pH. So that's why the appropriate amount of the acid is also important because otherwise they will be oxidized. Okay, so now we don't need to talk about this guy because this is easy. Otherwise, you will be feeling very boring. So what happened is you have a cysteine right there. Now, obviously, there are a couple of things will happen. Is that right? This is first scenario. This is second scenario, third scenario, and fourth scenario. But keep in mind, when you put 2O there, above 2O, it's biologically unavailable and it's undigestible. There is one thing I do want to say here, and the textbook did a very good thing, is tyrosine, a very good example. So tyrosine, we want to talk about this last tyrosine, last experiment, last reaction. So tyrosine, what is the tyrosine looks like? We need to know tyrosine. We have a OH there. So you have a CH2, C, NH2, H, and COOH.